So basically, if something makes a sound, or if anything emits any sort of wave, if the thing that is emitting the wave is also moving whilst it's emitting the wave, then the wave fronts get bunched up in front of it. So we will demonstrate this by just playing this. Got this siren, this person listening to an ambulance coming towards them, and we'll see waves coming from the ambulance, and the person won't hear anything until the wave reaches their ears, and we'll also hear how it changes as the ambulance comes towards and goes away from them. So it doesn't hear anything yet, and then now can hear some. Um, Basically, it's slow, but if you look behind, they're more stretched out than they are in front. So the ambulance driver will hear a different pitch to this. She's going to hear this pitch, and as soon as okay, all right, hang on. Right, all right. So hopefully, in the video, maybe I don't know. Hopefully, what the animation was trying to show was that as the ambulance was approaching the person, there was the waves were bunched up, and it was producing this high pitched sound because the waves were bunched up. Whereas the person as the ambulance was moving away from the person, then they were stretched out, and so it produced a low pitched sound. So um, I'll demonstrate it with another simulation which won't actually make a noise this time, and this time it's a galaxy. So we're gonna move the galaxy towards and away from Earth, and we can see the waves that people on Earth would be experiencing. So this is a galaxy not moving. Now, if it moved away from Earth with a certain velocity, then we can see that the waves is going to squash up the waves in front of it and stretch out the waves behind it. This is actually what we notice when we look at distant galaxies. Um, when we look at distant galaxies, we see that they're stretched out. The light that we're detecting is the wavelength has been stretched. The wavelength is longer than we would have expected it to be. So if it was moving
The
towards
wavelength will then increase with its stretching out then.
exactly, yeah. So if the object's moving towards us, then it sort of catches up with the wave. I might demonstrate. I'm going to draw it myself a little bit to demonstrate it, but I'm going to also give you clips. I'm going to share these animations with you. So if a wave source is moving towards the observer will see that the waves will experience the waves as being shorter, the wavelength as being shorter, and the frequency as being higher. So if it was a sound wave, the pitch would be higher. If it was a light wave, well, the color would be different. So, for example, blue is a shorter wavelength than red. So maybe it would be blue rather than something else. What we need is, let's just say for now then that the wavelength would get shorter, and we'll talk about the colors in a moment. If the object is moving away from the observer, then we can see they're getting. It doesn't quite show it here. Let me reset it. Can I move this? No, I can't. That's a shame. Can I? Okay. All right. You'll only see it for a short time because it's quite near the left-hand part of the screen. But there you go. So you can see how they're quite stretched out on the right and squashed up on the left. So if this is a sound wave, we'd experience a low pitch. So let me just take a snapshot of that one, and you'll have that one as well now. Okay. Okay, so with this one here then, so I'm trying to demonstrate it myself now. In this case, if the wave source was moving, was not moving, then the waves would just emanate outwards. The oldest wave would have travelled the furthest. So this would be, say, the first wave it's produced. This is the second wave it's produced. This is the third wave it's produced. And this is the most recent wave it's produced. And they're all centered around the same place because it's not moved since it made the first wave. Now, if on the other hand, then that it did move, then maybe when it made the first wave, it was all the way over here. Right? It was centered around that point, this point here, and then it moved a little bit to point to, and then it moved the next. So it was moving towards the right, and each time when it made the next wave, it moved a little bit further towards the right. So by the time it's made the most recent wave, then it's moved us all the way to here. So it's moved from here to here. This point here, which I will colour in pink, was when it made the first wave. But it since moved, it kept moving towards the right, and each time it moved, it produced a different wave. And that is why they end up being squashed up at the front and stretched out at the back. That's kind of what they're trying to show here. So what we noticed when we looked up at the night sky is that everything that we expected, whenever we thought that we're going to see a certain color wavelength, we in fact saw a different wavelength, and we saw. Well, if I had a chance, I'd explain this in a little bit more detail here, but roughly speaking, this is kind of like a fingerprint, like a sort of pattern from looking at all the light from a star or from a galaxy. And what we noticed is that everything was all the wavelengths were a little bit longer than we would have expected, and so we realized that this must mean that the object that's producing the light is actually moving away from us. And this is what we noticed when we looked at all these distant galaxies, that they were moving moving away from us. And this is the main bit of evidence for the Big Bang theory. If everything is moving away from us, then there must have been a point in the past when it was all in one place. Okay?
Yeah.